All right, so far this unit we've talked about characteristics of gases like volume, temperature, and how those characteristics affect pressure. Today we're going to look at the relationship among those variables for ideal gases. Remember, ideal gases are hypothetical gases. There are a couple gases that actually come close to being ideal gases, but not many. All right. So the ideal gas law, it demonstrates that the pressure of a gas is inversely proportional to the volume and directly proportional to the temperature. So remember, inversely means if one goes up, the other goes down, and directly proportional would be if one goes up, the other also goes up, or if one goes down, the second variable also goes down. We have this law, Avogadro's law, demonstrates that the volume or pressure is directly proportional to the number of gas molecules. So the formula here kind of looks like P1 V1 over T1 and N1, N standing for the number of moles of the substance, equals your P2 over V, or P2 times V2 over T2 times N2. Okay, so very similar to the formulas we worked with on Wednesday. The ideal gas law is a single equation that relates pressure, volume, temperature, and the number of moles. PV equals nRT, affectionately nicknamed Pervnert. This is the ideal gas law. This ideal gas law basically just rearranges that Avogadro's law. Your ideal gas constant is this variable N, and that's an R. Yeah, R, sorry.
What is that word up there? Is that number?
The number of a gas.
Oh, okay.
Number, can't read my scribbles. So the value for R is different kind of depending on the units you are working with. So here is your table. Your unit of pressure determines your unit or your value for R. Okay? So you'll have to make sure when you're doing these problems that you pick the correct R value based off of whatever pressure unit you're working with. Evaluating the ideal gas constant, the temperature must be in Kelvin. That seemed to be a titch of a struggle for some of you on the 14.2 problem. Some of you ran all of your problems in Celsius. It is conventional to use liters for volume. That's normal. And the value of R will change depending on the units used for pressure. So let us practice this. What volume is occupied by 3.76 grams of oxygen gas at a pressure of 88.4 kilopascals and a temperature of 19 degrees Celsius? Assume oxygen acts as an ideal gas. So the first thing we need to do is deal with this 3.76 grams of oxygen gas. And so nowhere in our PV equals nRT formula do we have a place to put grams of oxygen. Instead, we have to convert this 3.760 grams of oxygen into moles of oxygen. So 1 mole of O2 is how many grams of oxygen from the periodic table? 16, but we have to double it because there's 2, so 32. 32.0 grams O2. And here we get 0.117 moles of O2. So now our N, we've figured out our N value. Our pressure is 88.4 kilopascals. We don't know our volume. We have our N. R, which R value will we use, bless you, for this particular problem? Are we going to use the 8.31, the 0.08206, or the 62.36? Good, 8.314. And then lastly, our temperature is at 19 degrees Celsius, but we have to convert that to Kelvin, and you do so by adding 273, and that is 292 Kelvin. And then you can just plug everything into PV equals nRT. So our pressure is 88.4. We don't know volume. N is 0.117. R 8.314. And then T 292. So then 88.4 times V equals 285.25334. It is best practice not to round your numbers until the very, very last answer. You'll get the most accurate answer this way. To get V by itself, you need to divide out the 88.4. Do that on both sides. And your volume is 3.23 liters of O2. Make sure when you write your answer that you are putting your units. Some of you on the last assignment skipped your units, and that was detrimental to your success on that assignment. So we can find molar mass and density also by using this formula. The molar mass and density can be determined once the mass and the volume of a sample are determined, as long as temperature and pressure are known. So a certain reaction occurs producing gaseous oxide of nitrogen. The gas has a mass of 1.211 grams and occupies a volume of 6.77 milliliters. The temperature in the lab is 23 degrees Celsius with an air pressure of 0.987 atmosphere. Calculate the molar mass of the gas. Assume the gas is ideal. So we know our mass is 1.211 grams. Volume is 677 milliliters. Temperature is 23 plus 273, so that gets us 296. Okay. P was 0.987 atmosphere. Which R value will we use then? Good, 0.08206. And we do not know our N value. So we will use PervNERT, PV equals nRT, to solve for N. So our pressure was 0.987 times the volume. What do we need to do to the volume? We need to make it liters. How many liters is that?
100? Or,
Mm-mm.
is there 100 milliliters?
It's 1,000. So 0.677. And R times the temperature. And over on this side, it's 0.668199 equals N times 24.28976. At this point, you divide each side by 24.28976 to get N by itself. and N is, where did I write that? 0.0275. Are we done with this problem? No. We found that moles, it is asking us for molar mass. So remember that molar mass is grams over moles. The problem gave us the grams, 1.211, and we just calculated the moles, 0.0275. Do that simple division, and the molar mass is 44.0 grams per mole. All right, so the ideal gas law can be used to find the density of a gas when conditions are not at standard temperature and pressure. Do you want to go through the whole perv-nert aspect of this problem, or are we comfortable with that part? I need feedback, guys. We're good? Okay, so in this particular problem, using perv-nert, you would have to solve for volume. And the volume ends up being 25.74 liters. And so determine the density of ammonia at this pressure, at this temperature, assuming that it acts as an ideal gas. So density is mass over volume. And the mass is not given to us, but ammonia is NH3. So we can use our periodic table and say, all right, nitrogen's 14.007 plus 3 times hydrogen, which is 1.0079. So our mass of ammonia is 17.0307. We can throw that into our density formula then over the volume, which you would have calculated using perv-nert. And your density is 0.662 grams over liters. Moving on. They do get a little more complicated because we can use stoichiometry when things are not at standard temperature and pressure. Stoichiometry, remember, requires a balanced chemical reaction before you can do any of the math. So, what volume of carbon dioxide is produced by the combustion of ethanol? So you need to write the reaction for the combustion of ethanol. They give you the formula for ethanol is C2H5OH. Combustion means you're mixing it with oxygen, and your products are always carbon dioxide and water. And so we need to balance it. Do you guys need to practice balancing it? Do you remember how to do it, or can I just give you the numbers? You know how to do it? Leroy, you're good with just getting the answer? Okay, maybe 3 and a 2 and a 3. So once we have that balanced, we can see what bits of information we're missing. We have pressure is 728 millimeters of mercury. Volume we're being asked to find. N, they don't give us N either. And R, we can pull R from the table. We'll use the millimeters of mercury value. And T is 54 plus the 273. And that gives us 327. So how are we going to solve for N? We need to figure out N before we can figure out V. Yep, so like all good stoichiometry problems, you start with what you're given, 25.21 grams of ethanol, H5OH, and you convert that into moles of carbon dioxide because it wants to know the volume of carbon dioxide. So 1 mole of C2H5OH, and the mass of that, when you do your molar mass, it's 46.08 or 0684 grams of C2H5OH. Then we use our molar ratio to go from moles of ethanol into moles of CO2. So we have 1 mole of ethanol from here, C2H5OH, to 2 moles of CO2. And then the last step is, actually that is the last step because we need to be in moles of CO2. And we'll get 1.09 moles of CO2. So now that we have our N value, you can use PV equals nRT to solve for volume, which I'm assuming you're comfortable with that step. Volume is 30.53 liters. All right, last couple things. Real gases and ideal gases. An ideal gas follows the gas laws at all conditions. Real gases are pretty much will follow the gas laws, but only at STP. A real gas is a gas that does not behave according to the assumptions of the kinetic molecular theory. Conditions normally found in the lab allow real gases to behave like ideal gases. So when do gases behave least ideally? This would be when the pressure is high enough to diminish the empty space between gas particles. It's forcing them to be very, very close. Or when the temperature is so cold that the particles slow down. Gases are most ideal at high temperatures and low pressure because they have weak attractive forces. It allows them to be very spread apart. Ideal gases have a value of 1 when looking at the ratio of PV to RT for all temperatures and pressures.